This is part 2 of lesson 5.2 on the extreme value theorem. We are going to finish up our discussion of the extreme value theorem by doing a couple of examples and then talking about the definition of critical numbers and doing some examples of those. Okay, so example 5. For each function shown below, justify why the extreme value theorem, the EVT, can be applied or why it does not apply on the given interval. So that's the first thing you should do, is determine whether or not the EVT can be applied. So just to review real quick, let's see what the conditions are for the EVT. So the EVT has to be continuous on a closed interval, has both a max and min on the interval. Okay, that's all we're looking for the EVT. The conditions are a little less stringent than they are for the MVT or the IVT. We have all these VT theorems. Okay, so for letter A, our interval is -4 to 4. So let's see if the function is continuous on the interval. And right away you can see here that x cannot equal 2, which is in the interval. So we would say that the EVT does not apply since f of x is not continuous at x equals 2 and our interval is -4 is less than or equal to x less than or equal to 4. Okay, letter B. Letter B, g of x is e to the x minus 2 plus 1. So this is a continuous function. This is continuous on the interval. It's continuous everywhere. Okay, so the EVT applies. Okay. We're not finding the values, we're just deciding whether or not it applies. Okay, letter C, h of x equals x times the square root of x plus 2, and our interval is -6 to 6. The problem here is we want to remember that our square root, that x plus 2 has to be greater than or equal to 0. So x has to be greater than or equal to -2. So h of x is not defined from -6 up to -2. So the EVT does not apply. Because that section of the graph is in our interval, so it doesn't cover the whole interval. Okay, now we've been flirting around with what a critical number is for a while, so let's formally define it at this point. A critical number or value of a function is an x value, and we call it C for critical. But the important thing you want to remember is it has to be in the domain of f, such that either f prime of c equals 0 or f prime of c does not exist. If x equals c is a critical value, then c comma f of c is called a critical point. Okay, now the first thing that I highlighted there, c has to be in the domain of f. It is possible that when you take the derivative, that points that aren't defined in the derivative are defined in the original function. But if it is not defined in the original function, it doesn't matter if it does not exist in the derivative. It has to have been part of the domain. Okay, so going along with what we told for our extreme values, or our absolute mins and maxes, Relative and local extrema can occur only at a critical value on an open interval. The absolute or global extrema must occur at a critical number or at an endpoint, okay? Because remember, we're looking at sign changes and differentiability, so we don't include endpoints. So that's why critical numbers have to be on an open interval. But if we're just looking for absolute extrema, they can be at the endpoints. Okay, now, how do we go about finding these absolute max or mins? And one way is to use a candidate's test. And what we're really doing is making a chart of possible values. So here is the process we go through. We're supposed to find the absolute extrema of the function on a given interval, provided the EVT is applicable. I never like that word. If it is not, justify why. Well, it is definitely applicable in letter A because we have a polynomial. So it is definitely continuous on that interval. All right, so what we need to do is we need to find the value at the endpoints. So we're going to find f of -1 and then we're going to find f of 2. Now you notice we can use a calculator for this. So I'm just going to write down what the values are. F of -1 is 0, and f of 2 is 36. Now the next thing we want to do is take the derivative, because we want to find our critical numbers. Because relative mins and maxes occur at the critical numbers. The absolute ones can occur at the endpoints or the critical numbers. So we need to find those critical numbers. So taking the derivative, we get 24x squared minus 6x minus 9. And critical numbers are zeros of our derivative. And factoring this, we can factor out a 3. We get 8x squared minus, 2x minus 3 equals 0. And this factors into 4x minus 3 times x plus 1. Is that right? No, that doesn't seem right. Nope, I forgot the 2. There should be a 2 here. 2x plus 1. Okay. So our critical numbers are at 3/4 and at -1/2. Now here's where the candidate's test comes in. So what we're going to do is you just make a chart of values here and you put them all in order. So our first endpoint, our lowest endpoint is -1. The next point we come across is -1/2, and then 3/4, and then finally our other endpoint is a 2. So we know that we start at 0 and we end up at 36. Now what we have to do is substitute our critical numbers into our function, our original function, and find out their values. So f of -1/2 is 4.75, and f of 3/4 is -3.063. Now what you do to find the absolute extrema is pick the largest point and the smallest point. Okay, so our absolute max is at 2,36, and our absolute min is at 3/4, -3.063. Okay? All right. So what I'm going to do is I'm going to write the answers for B and C, and then let you guys pause the video and do those two, and then I'll finish up with D and E because they're a little different. Okay, so there are the answers for B and C, and if you notice, C has 2 absolute maximums, which can happen, especially when you have trig functions, things that have a cycle or a period. It is possible to have more than one absolute max or min, so you need to list them. And it's good that we're on a closed interval because there are actually an infinite number of maximum and minimums for h of x for that function. Okay, so let's go ahead and do letter D and E together because they're a little different. So letter D, since we have a log function, there are values where log is not defined. So on our interval -2 to 5, f is not continuous in that interval. And you can check that on your graphing calculator. And what you're looking for is the fact that it is not defined from negative numbers all the way up to 3. Because log has to be, remember, ln of x has to be greater than 0. Okay, so anything negative, and this will equal 0 at x equals 3, and also -3, but that's not in our interval. So anything before 3 is going to be out till you get to -3. It's going to be a graph that's going to kind of look like this, I think, like that. Okay, so this whole section in the middle here is undefined, and our interval, because this would be -3 here. So our interval starts like right here and continues over this way. So there's a section there from -2 to 3, which would be right here, the pink part, that the graph is not defined. So the EVT does not apply. So it is important that you have an understanding of what basic functions look like. And I know it seemed silly last year that we spent so much time on that in chapter 1, but it does come into play. All right, letter E. Now we have a cube root function. We have a radical. So how does that work? Well, the nice thing is that it's a cube root, so it's defined everywhere. So we definitely can apply the EVT. So we can start by finding the endpoints. So h of 1 is going to be the cube root of 1 minus 2 squared. And when we do that, we get a 1, of course. And h of 10 is going to be the cube root of 10 minus 2 squared, which is the cube root of 64, which is going to equal 4. Okay, so now we have to take the derivative. So h prime of x is going to be 2 over 3 times the cube root of x minus 2. Okay, and then what we can see here is that x cannot equal 2. So, and that is on our interval, and that's what I was talking about when we defined critical numbers, is 2 is allowed in h of x, so it is in the domain, but it is not allowed in the derivative. So that makes it a critical number because it's an undefined value of the derivative. So now we can make our candidates test table, and it's a small one. We just have our endpoints and our one critical number. And so at the endpoints, we already know we have 1 and 4. And if we substitute 2 in, we get 2 minus 2 is 0, so we get, all right, so like we did in the one at the beginning, here is our largest value, here is our smallest value, so our absolute min is 0 at x equals 2, and our absolute max is 4 at x equals 10. Okay, if you have any questions, especially on parts B and C, we will go over those in class, and I'll answer any questions then.